Hi everybody, this is Aaron Corcoran again. Welcome to another tutorial on using ThruTracker. This tutorial is going to walk you through the process of generating a 3D calibration. More specifically, this is determining the camera extrinsics, basically the positions and the orientations of the cameras in the field, which is required for generating the 3D points that you're going to use from our 2D detections. Now, to begin this process, you're actually going to use a complementary piece of software called DLT DV8. This was developed by Ty Hedrick at the University of North Carolina, and you can install this on Windows, Linux, Mac computers without any licenses. So the first thing you're going to do is open up DLT DV8, and this is downloadable for free at Ty Hedrick's software. I'll send you links for that. And open that up, and it should generate this app here. So we're going to start a new project. So you just go to Project, New, and I'm not going to walk through all of the details of this software. Ty has some lovely tutorials on his website, and I highly recommend you familiarizing yourself with the software and those tutorials as well. So I'm just going to show you the step-by-step process specific to generating a 3D calibration using a wind turbine. So we're going to do a new project, and we're going to do 2 videos. I'm assuming that you're using 2 videos for this. And now we're going to find our video files. It should be a master and a slave. And I'm going to find those files. So I'm always going to pick the master first, and then the slave second. And now it's opened up these videos, and it's asking me if the cameras are calibrated via DLT. The answer is no, because that's what we are doing right now. Once we've calibrated them, then we can add that, but right now they're not yet calibrated. I'm going to say no. This opens up a time series so we can see different points that we have already tracked. I'm going to minimize that for now. And we've got our 2 views of the camera. And basically what we're going to try to do is digitize points that we can determine are the same exact point in each of our views. So this is the first frame in the camera, and I'm just going to leave a single point. So in DLT, you can have multiple points. In this case, I'm just going to track a single point and advance through different frames for digitizing the different locations of objects that we're tracking. So you don't really have to do much here. All you need to do is zoom in on the individual points you want to track and digitize them. So there's some shortcut keys in DLT DV. You can use the plus to zoom in. And I'm going to start by tracking this little antenna looking structure. The end of it gives me a very nice discrete point that I can determine precisely the same position in 3D space in each of my cameras. So you just click on the point in each of your views, and I'm going to select the other view here and zoom in on the same point, and it zooms in on the location where your mouse is. So I'm going to click that, and that's my first digitized point. Now I'm going to advance a frame just by using the F shortcut key. You have to have your mouse over the window again, so that's going to advance. Now I'm in the second frame over here. You can see that I'm selected. And now I'm going to choose another point, maybe the other end of this antenna-looking structure. Click on that, zoom in, and I've got those 2 points. And the goal here is you want to get as many points as possible that are covering the full view of the camera in both 2D and 3D space. So these are 2 points that are fairly close together. If you press R, that's going to zoom out. And you can see there's 2 points that are pretty close to each other. So you don't want to do too many points in the same view that are very close to each other. So you wouldn't want to go frame by frame and digitize these same exact points. It's not really adding anything to the calibration, and there's more potential to cause problems if you have a given point that wasn't digitized accurately. So you might be tempted to find certain points, such as the hub, which is a curved structure, and it's actually pretty difficult. So in this view, I can determine that the tip of the hub, I can see it pretty well, so I could use that. in this view, it's pretty difficult to know exactly where the same three-dimensional point, the point in 3D space is in each view. So I'm going to avoid those kind of points. Instead, I'm going to look for objects that have a discrete location. So the back of the nacelle here comes to a bit of a tip. So I'm going to digitize, first I'm going to advance a frame, and then I'm going to digitize the center of that point right there and find the same point here. And that's pretty good. I've got 3 points, and those are all within pretty close 3D and 2D space. So I really wouldn't want to do too many that are close to those locations. So next, what I'm going to do is go through the video and try to find orientations where you can see different parts of the turbine in different locations and digitize different locations. So we can advance through the frames here using this scroll bar. And this looks like a good place where we could digitize some other points. So again, we can do the tip where it's converging here on the back of the nacelle, and do that point. Zoom in. It's a little difficult to determine exactly, but I think we can get within a pixel or two. And I think this antenna is at the same location, but I can't quite tell. I could even use, there's a little bit of a hot spot right here. That's an okay point. So I'm going to do the center of that little hot spot. Whoops. And I forgot to advance a frame. So I'm going to go back and now advance a frame by using the shortcut key F and do this little point here. That looks good. And I'm going to advance another frame and zoom out. And now, looks like this is a position to use the turbine tips. Now, the turbine tips can be tricky because in three-dimensional space, it can be difficult to know exactly where the tip of that turbine blade is. But this looks like a pretty good orientation. So I'm going to, again, advance a frame and click on what seems to be the very tip of that turbine blade. Zoom way in and do that same point. Now, what I'd like to do is take advantage of the fact that these turbine tips are moving, so I can do Shift F or Shift B to go back or forward 50 frames. And I'm going to increase the number of frames that we can see here so I can see where that last point was. And now I can see that that turbine tip has moved that amount. So we can just do another point here. I want to be as careful as possible to get a consistent position in 3D space. And now we can advance another 50 frames and do this point and this point. And again, it really doesn't help if you're doing the points very close together. So this is a pretty good spacing here. And I would take advantage of this and do as many points as we can. And so we can now in this second view here, I've lost that turbine tip. So you're going to be kind of limited in some cases, but I can go back. I'm just doing Shift B again and get as far as, say, here. And this is going to get some different locations in 3D space as well as 2D space. Fix that a little bit. So I do all of these points every 50th frame in this case and fill in the different locations. And by the end of it, you should do your best to get all those 2D points. So see if you could get an orientation where you have the turbine tip up in the corner over here. And I'd recommend a total of maybe 75, 100 points to work with. I'll show you an example in a second here where we used about 65, 67 points, and that seemed to work well. But it's important that each point you digitize as accurately as possible and that that's covering the 2D and 3D space as best you can. So when you're done, you can go up here and you can save the project so that you can load that back up again. And we could just call this NREL test calibration. I've already saved this, so I'm not going to actually save it in this case. I'm going to hit cancel. And then you also want to export the 3D points. So you go to a points, export, and we'll do NREL test calibration and choose a location on your computer where you know you're going to be able to find that. And I'm sorry, actually in this case you want to just choose the folder and then you put the name of the file in this little dialog box. So NREL test calibration underscore DLT DV8 data. And then I'm going to hit OK. And you want to save it in the sparse format. That's very important. This will save a lot of space on your computer and time for opening and closing the files. And then that's saved here. Okay, now we're done in DLT, so I can actually close that out. And next we're going to open up ThruTracker and do the calibration. And for this, you're going to go up to open up ThruTracker and go to Tools, Make 3D Calibration. And this is a little app that Ty Hedrick also made called Simple Wand. This is a variation of another project that he worked on called Easy Wand. This is customized for the needs of doing these 2-camera scene calibrations at wind turbines. And so the calibration, the way that it works is, I'll show you the essential parts of doing this type of calibration. There's a number of features that we may or may not use here. So first, you're going to do a new project. So project, new project, and it's going to ask how many cameras you have. So you're going to put in 2. This is really only set up for 2 camera calibrations in Simple Wand. If you have more than that, then you're going to need to use Easy Wand within MATLAB. But in this case, we're using 2. And it has different options here. There's paired points, which we're not using. That would be like if you had a wand with 2 markers at either end of the wand. Here we're using unpaired points. So we're going to choose this unpaired points tab. And then we're going to load in our data. So we're going to do data, load unpaired points. And this would be the data that we just digitized using DLT. And I've got some example data in here for a calibration, so you can try that out by going to within the ThruTracker folder that you've installed it within. You go to example data and then example calibration data and choose the unpaired points. I'm going to select that. And that has populated this matrix with the data that we've digitized. So we can scroll down and see that there were 67 points that I digitized. And this is showing the positions within each of those cameras. So you can see camera 1 and camera 2, each of those points, the X and Y, or in this case, U and V coordinates of where each one of those points was digitized. So that appears to have loaded properly. Next, you're going to go up and do data, load a camera profile. And this is going to load the intrinsic camera information for your cameras that is generated using the thermal camera calibration app, also in ThruTracker. So there is another tutorial that I've made for that, and you should check that out if you need to make your own intrinsic camera profile. But we already have one here, so I'm just going to load that, and again, go to example data, and then example calibration data. And these cameras were FLIR A65 and using a 25mm lens. So we have that camera profile here. I'm going to select that and do open. And that just populated all the information we need about those cameras down in the bottom here. So there's camera 1 and 2. They're both listed as primary. The principal point, which is the center of the optical field of view on the camera sensor, is determined. The focal length, in this case, which tells you the amount of magnification that the camera has, which is determined by the sensor size and the size of the lens on the camera, as well as the camera distortion. So again, all of this is the information about the camera that you need for the calibration itself that is generated using the thermal camera calibration app within ThruTracker. But for our purposes, all you have to do is load that, and we are good to go. So now the next step before we do a calibration is we want to align and scale the scene. So we go over to this tab here, and there's a number of options, but the default option is camera azimuth and elevation, which is what we're going to be using. And the azimuth of the camera for this is all based on the reference camera, which is going to be the last camera in this case, camera number 2. So in the field, you could measure what direction that camera is facing and put that information here. We're not using that for our purposes, so I'm just going to leave that as 0. You also want to measure the elevation angle of the camera. So how far from the horizon is the camera pointed up? In this case, we measured that in the field at 60.3 degrees using an inclinometer. So you put that information in here. And then to set the scale of the scene, so we know how far things are apart, then there's this option here for set the scene scale from the measured camera distances. And that just means we are setting the scene size, the scale, based on the distance between our 2 cameras. So in this case, we set those cameras at 30 meters apart. So you can set that here in camera distance. And now we're ready to go. So the next step, all you have to do is go up to operations, and we're ready to compute our calibration. So you click compute calibration, and voila, here is our calibration scene. So this is showing the determined locations and orientations of our 2 cameras. So they are pointed up. You can see at about a 60-degree angle like we talked about. The scale was set. So you can see that these 2 cameras are indeed set at a scale of about 30 meters apart. And then all of these green dots are each individual points that I digitized like I showed you before. And you can see there's 3 clusters of dots. This cluster in the middle are different points that I digitized on the hub or the nacelle. Then these points at the end are different turbine tips that I digitized in different parts of the camera. And then the closer points are the turbine tips that were pointed toward the camera. So you can imagine that the cameras have a cone-shaped field of view. The further away you get, the wider that field of view is. And that's kind of illustrated here because the turbine tips that were in view of both cameras were only within this relatively narrow 3D range, whereas further away that those points spread out. You can see we've done a reasonably good job of covering the points in the 3D spread. So you should try to get something that approximates this. Now, in generating our calibration, the main thing that you want to look at to see how well it worked is the DLT residuals. So that's shown down here, and these are in pixels. So our DLT residuals for this calibration were just under 1 pixel, which is not bad, but we may be able to do even better. So the next thing that we're going to do is go back to our unpaired points, and now we see that we have X, Y, Z coordinates for each of those points, and there's an error. This error is the difference between where that point was digitized and the reconstructed point using the calibration. So lower error obviously is going to be better. So what I'm going to do is sort all of these points by the error, and we can see that a number of points have considerably higher errors than the rest of them, and we might consider these to be outliers. So our average error was about 0.9, just about 1. And these errors that are more than double that, we might consider those to be outliers. So we can click on the ones we want to get rid of. And in this case, I know that some of these are likely to have some error because it's difficult to know the precise position of those turbine tips. So I'm going to be fairly liberal and taking out up to maybe 20% of the points. You want to be careful here and not overfit your model. But in this case, I'm going to take out all of these that are above 2. And now we can do the operations and compute calibration again. And it's going to recompute another calibration. And it's taken out those outliers. And now our DLT residual is considerably lower, under 0.4 pixels. So I'm pretty happy with that scene. You can also look at the scene and determine if the scale appears appropriate. So I know in this case that the hub is about 80 meters above the camera 2. And in this case, we can eyeball it and see that camera 2 is at about minus 70 meters, and the hub and the nacelle points, the center of those are about 10 meters. So those are indeed about 80 meters. You can also determine what is that distance between the hub and the nacelle and your scatter of points. In this case, it is matching up to what I would expect. So I'm pretty happy with that calibration. Now, the final step is we want to save this. So you can do project, save this project, and we can choose our location where you want to save that. We'll go NREL test 3D calibration. So we can load that back in later on if we want to check anything or change anything. Save that. As well, we want to export the DLT coefficients, and we'll use that later on for generating our 3D tracks. So I'm going to save that as well. NREL test 3D calibration. Do save, and we've exported our calibration. So that's it. That's how you generate a 3D calibration using DLT-DB and SimpleWand. Thank you, and we'll see you in the next video.